traveling forward further into the Archean. Well, to the end of the Archean, about 2.5 billion years ago is where we're going to start. But before we start there, I want you to look at this image and look at those rock-like mounds on the bottom of the image. And they're actually alive. Those are mats of cyanobacteria, blue-green algae-like organisms. So what do? They have the enzyme rubisco in them. So they're able to fix carbon. So they take in carbon dioxide, use energy from the sun, and to form biomass, and they let out oxygen and water vapor as a byproduct. So they're photosynthesizing. These mounds are stromatolites, and they're a major reason why you exist today and why the modern atmosphere looks the way it does. So they are producing oxygen. And so let's think a little bit more about what is actually happening. So these stromatolites are under the water in the ocean, and they're photosynthesizing, taking in carbon dioxide, releasing oxygen. This oxygen is beginning to accumulate in the water. And once the ocean becomes super saturated in oxygen, guess what? It's going to want to travel from an area of higher concentration to an area of lower oxygen concentration following Fick's law of diffusion. So it's going to outgas and start accumulating in the atmosphere. But while we're getting oxidation in the ocean, it's going to change the way geological processes or chemistry is happening in the ocean. It's altering the chemistry. And we actually have solid geologic evidence showing that exactly when this great oxidation event occurred. And it is preserved in something called a banded iron formation, which you will see above my head on the right. And these are beautiful, beautiful stratigraphic formations. And what you can see is the sedimentary layers. You see alternating dark layers and lighter red layers. And this diagram on the left is going to show you in a little more detail exactly what the chemical processes going on in the ocean at this time look like. So we have some cyanobacteria in the photic zone. So the photic zone is the depth at which you could still get sunlight in the ocean. And we have some Fe2 and Fe3, so this is iron, and also some silica in the ocean, Si, and silicon is Si. And what is happening is they are reacting with the oxygen. They're becoming oxidized. So the iron is becoming oxidized. And what you're getting is you have some iron combining with silicate, and you have some oxidized iron silicate. And you see on this figure 3 right here that they're accumulating in alternating layers on the ocean floor. So in this image, the dark gray layers are the silicate, and the reddish layers are the iron, the oxidized iron. Because remember that when we talked 2 weeks ago about chemical weathering, one big major process we talked about was chemical oxidation. And an example of that is when iron becomes oxidized, it looks red. When iron becomes reduced, it looks more green. So we're going from a reducing environment to an oxidating environment because of this accumulation of oxygen in the water. And so the reddish layers here would be the oxygenated, oxidized iron layers. So that's what it shows in this cartoon here. I think in this image up here, this is a slightly different case. I think our oxidized hematite or magnetite layers would be these darker grayish red layers, whereas the red layers here would be chert, which is a silicon with some iron impurities that make it look red. But Anyway, we have this evidence preserved in banded iron formations because it wasn't until this time during the Great Oxidation event 2.5 billion years ago that we start to see red show up, red rocks, oxidized iron. Now, here's a summary of Earth's 3 distinct atmospheres. So remember, Earth's atmosphere has evolved over geologic history, and it has developed 3 distinct atmospheres in the last 4.54 billion years. So starting at the top, we have our first atmosphere, which was very thin because Earth was extremely hot. We had molecular hydrogen and helium, and these molecules were able to move fast enough where they could exceed the escape velocity requirement for Earth and drift off into space. The second atmosphere is due largely to volcanic outgassing. So we have water vapor, carbon dioxide, and ammonia outgassing from these volcanoes. But then we have our stromatolites, and they're consuming energy from the sun and carbon dioxide to produce oxygen. So this oxygen started to build up in the atmosphere eventually. And so this brings us to our third atmosphere. And so carbon dioxide continued to decline due to this cyanobacteria. Ammonia molecules were broken apart by reacting with sunlight, leaving dinitrogen gas and molecular hydrogen. Most of the molecular hydrogen drifted off into space, but our atmosphere is mostly, it's 78% molecular nitrogen, because molecular nitrogen is something that we call an inert gas. It doesn't react with other gases, so it's abundant in our atmosphere. And of course, we still have carbon dioxide from respiration and outgassing, and today from fossil fuel, burning of fossil fuels. So the organisms on Earth play a huge role in actually dictating what its atmosphere looks like. So there's an interaction there, very important interaction. Just remember that we have the atmosphere, the biosphere, the hydrosphere, and the lithosphere, and they don't act in isolation. They all impact one another.